Welcome you all in this new video, and today video is going to be very interesting because in this video we are going to discuss about the magnetic field. Okay, at any point because of a straight current carrying conductor. What does this mean? This means that there is a conductor, okay, in this is the structure of straight line, or we can say straight conductor, and current is flowing through this straight conductor, because of which it produce a magnetic field. We know that, like you have listened that right hand thumb rule. It's your thumb, okay, and here is your curling of the finger. The curling of the finger represent the magnitude of the magnetic field, okay, or direction of the magnetic field. And what does this thumb represent? This represent the direction of current, okay. So in this video what we are going to do, we are going to calculate the derivation for magnetic field magnitude at a particular point, okay, at a distance from the straight conductor, okay. There is a straight structure conductor or a straight current carrying conductor, and in surrounding there is a particular point. On that point, what is the extent to which there is magnetic field because of the current flowing on this conductor, okay. So this is our the thing that we are going to derive, okay. And let me write the expression, okay. I will write in the last. So first of all, you understand what does the meaning of our topic, okay. It means that you have a straight conductor, okay, which is carrying particular amount of current within it, okay, and because of current carrying conductor, in its surrounding there is magnetic field produced by it, okay. And we have to calculate what is the expression for that magnetic field, okay, which is going to be produced in the we can say in the proximity of this conductor, okay. So let's start our video. So we will segregate our video within the two sections. So first section we will discuss about the consideration, okay. In consideration, what we are going to discuss, we will discuss consideration and approach, okay. I always divide expression in two elements, okay. First is consideration and second is approach, and after that we apply both these to derive that equation, okay. So first of all, understand what is the consideration. Consideration is nothing. There is what we are going to consider, that is consideration. We will consider a straight conductor, okay, and we will consider that a particular amount of current is flowing through that conductor, okay. So this is done. So now what we will choose a middle point, and we will also choose let's say a point at a particular distance from the center or from that particular conductor, okay. Let's say that is R. This is not actual diagram, it's just to give you the idea what we are going to consider, okay. So it will be easy for you to correlate the diagram with the expression, okay. So this is the expression. So we will consider a point here, and then we will calculate the magnetic field because of a small element of this conductor, okay. And we will consider a small element, and because of this element, what will be the magnetic field at this point, okay. So that is we are going to calculate, and when we are with the magnitude of the magnetic field because of this small element, then we will integrate that expression with the limit, okay, with the limit through which we can calculate the magnetic field because of this whole conductor at a particular point P, okay, whatever it is, P at a particular distance, okay. So this is simple approach. Means first we will calculate the magnetic field because of a small element that we are going to consider. So after, when we get the equation, so after that we will integrate it to get a generalized equation for the whole conductor, okay. What is the magnitude of this whole conductor in a surrounding point, okay. So this is our consideration. Now understand what is our approach. What is the approach means, what are the steps that we are going to follow in this equation, in this expression, okay. Approach is very simple. We will use the Biot-Savart's law. Biot-Savart's law, and what is this is most important and first law which describe, okay, what will be the expression for magnetic field at a particular point, okay, outside the conductor. Okay, conductor means through which the current is flowing. Okay, so he gave the expression that is dB is equal to mu naught over 4 pi, okay, IDL sine theta over r square. What does this mean? This means that IDL is that small current element, okay, and what is the r? R is the distance of that point where you are going to calculate the magnetic field because of a particular conductor. Okay, that is r distance, and theta is the angle made by the, we can say, the radius vector or the distance vector with respect to the inclination of that conductor. Okay, so Biot-Savart's law we will use, and this is our consideration. I hope consideration and approach, both the steps are clear to you, and now it is very easy for you to understand how we are going to calculate the equation for magnetic field because of that particular conductor, straight conductor, okay, which is carrying some amount of current, okay, and because of which there is magnetic field around it. So we are going to calculate the magnetic field for that. Okay, so it is very easy and it is very interesting. You can say that there is a magnetic field, okay, so sorry, there is a conductor, and let's say, let me draw a diagram. First of all, understand guys diagram completely. If you understand your diagram completely, then there is no need to, you know, remember any facts, we can say, and mug up any formula. So let's say this is our straight line conductor, and it is very beautiful guys. Look at here, it is your conductor or straight line conductor through which the current is flowing, and you are calculating the equation, okay, generalized equation, which you can apply anywhere, okay, in case of straight line conductor. So how important and how interesting it is while we are deriving the expression for it. Okay, so let's say here is a point P. Okay, I told you what is the consideration, so I am not going to explain now. So this is the distance, let's say this is r. Okay, let's say this small element, current carrying element, I told you that this is flowing through some current, that is I. Okay, I is the current which is flowing through this conductor. Okay, so don't be confused. So this is our conductor. Okay, this is our conductor. So here is the point P, and here is the small current element. I told you what is the magnitude of that current element, IDL. Okay, and what is the distance of that current element from that point P where we are going to calculate the magnetic field because of this small element. Okay, let's say this is small r, and let's say this point is the center of this conductor, okay, straight line conductor, and let's say the distance between the center and the current carrying element, that is small element that we had taken, okay, so that is L. Okay, so this is the expression. Let's say this makes an angle of theta, and here it make an angle of phi. Okay, let's say, and we know that this is 90-degree triangle. Okay, so what we can experience or what we can measure from this triangle OP, let's say this is B, okay, this point, and O point is here. IDL is nothing, it is the current element that we had considered, okay, that small current element. So from triangle, okay, OPB, what we can calculate? We can calculate the value of theta. What will be? It will be 180-degree minus 90-degree minus phi. So it will become 90-degree minus phi. Okay, so this is the value of theta. So we will use this value theta while we will explain, or while we will when we will do Biot-Savart's law. Okay, so this thing, I hope you are clear with this. Okay, so now by using the Biot-Savart's law, I told you what is our approach that include Biot-Savart's law, okay, through which we are going to calculate the whole derivation. So by using Biot-Savart's law, okay. So Biot-Savart's law says what? This is magnitude of the magnetic field because of the small current element, that is equal to mu naught 4 pi IDL, okay, sine theta over r square. What is the r square? R square is the distance between the current carrying element and the point where we are going to calculate the magnetic field. Okay, so from here there is sine theta. Now replacing this value of sine theta, okay, I told you that this is the value of theta that we have got from this triangle. Okay, so this is a mu naught over 4 pi ideal sine 90 degree minus phi over r square. And you know that what is the value of sine 90 degree minus phi? It is always equal to the cos phi. Okay, so our dB will be equal to what? Mu naught 4 pi, okay, and IDL cos phi. Now the angle has been gone changed. Okay, first we have the angle theta, now we have angle phi. Okay, so here is r square. Now guys, look at here. So this is our Biot-Savart's law, or we can say the magnitude because of that small current element at the point P, but it is incomplete. Okay, it is not complete yet, it is incomplete yet. Okay, so what we have to fill here so it can become complete? We have to fill here the value of cos phi, okay, and value of dl. So how we are going to derive or calculate the value of dl and cos phi? Through this diagram. Diagram is very important, guys, so that's why always keep diagram in the center, and by looking at the diagram derive the equation. Okay, so how we are going to derive the dl? Where is the L? L is here. Okay, so use the trigonometry formula here so that we can get dl. How you can get the dl? If we take that tan phi here, okay, so tan pi is what? Length over base. So here L will be equal to r tan phi. Okay, by differentiating this equation, so we will get dl r secant square phi d phi. So this is the value of dl. Now we have to calculate the value of d cos phi. So what is the value of cos phi? It is very simple or very easy. So that is equal to, cos phi is always equal to what? Here is what we can say. So either you can calculate the value of cos phi, or you can calculate the value of r square. Okay, and what is the value of cos phi is? From here you calculate it, it will be become your r over small r. So here if we calculate the value of small r from here, so it will become r over cos phi. Okay, so this is the value of r. Now we got the value of r, dl, and cos theta is also okay. We are not going to change the cos phi. Okay, we will replace the r square values. Okay, so r square value will become will come in the form of cos phi. Okay, so by putting all these values here, what we get, okay, let me do it in the next slide, so don't forget it. Okay, so what was our equation? So it was dB is equal to mu naught 4 pi, okay, and here was ideal I dl cos phi over r square, and we got the value of dl from the previous differentiation, that is r and secant square phi d phi. Okay, and we also got the value of r, that is r into, okay, we can say cos phi. Okay, now putting the value of dl and what is the next term? Dl, and here is r. Okay, putting the value of here. Okay, so we will get this, and what is the value of I, and dl is r secant square phi d phi cos phi over, and what will we get? Here we will get what we can say, this is the r square. So r square is what? R square, okay, small r square into cos square phi. Okay, so this is the value of cos square phi. So while we will doing it further, so it will become mu naught 4 pi. So it is very easy, guys. Always try to solve the equation, okay, within a very, we can say, every step, because it gives you confidence. Okay, it will increase your, we can say, thinking capabilities, how to distract, how to neglect the things, how to do it. Okay, so here we will become, so it will become if you take this thing in the denominator, so it will become r, okay, r1 r and this is r1 is cancelled from here, so here will become cos square phi and cos cube phi d phi, because here is phi, it will go upward. Okay, so here if we calculate it further, so this is our, okay, here is also I, so don't forget it, I over r, okay, multiply, and here is cos phi d phi. And what is the value or magnetic field for that small current element? Okay, because of that small current element, this is the value, okay, that will be experienced at the point of P. So this is value 4 pi, and let's extend I over r cos phi d phi. So this is the expression for that small magnetic field, okay, that is produced because of that small current element that we had considered. Okay, so this one current element, this current element have this, okay, magnitude at particular point P. Now I told you when I was telling you that what is our consideration, okay, and I told you that, so let me write first of all that what is the magnetic field that we are going to experience at point P because of that current, small current element. Okay, so this is 4 pi, okay, I over r cos phi d phi. So this is the, let me draw that diagram. This was our center, okay, this was point P, and this was that small current element IDL, okay, and it was angle phi. Okay, so I am not taking here angle, I am taking only the angle that is making by the P, okay, with respect to the center distance and that radial distance. Okay, so now calculate. So let's say this makes an angle with the, you know, bottom end and with the top end. Okay, we will integrate this equation with the angle that is making by this point P with respect to the, we can say, bottom end and also with the top end. Okay, so this is our limit, okay, through which we have to integrate this equation, so that we will get the equation or generalized equation for the whole conductor, okay, for the magnetic field that is experienced by the point P because of this conductor, because this conductor have a magnitude of current is high. Okay, so while for whole conductor, for whole conductor, okay, we are calculating now the value of magnetic field because of the whole conductor at point P. So what is our limitation? So that is phi 1 to phi 2, because phi 2 is the angle made by the P, okay, made at point P with respect to the upper end, okay, of that magnitude. So here you will become, it will become mu naught I over 4 pi r cos phi d phi. While you will calculate or integrate it further, so it will become mu naught I over 4 pi r, okay, and it will become, if we are putting it in this limitation, so it will become sine, we can say phi 1 plus sine phi 2. I am directly integrating it, okay, you just do it very briefly, okay, so you will get the understanding of integration also. Okay, I am putting it directly here. Now doing it further, so it will become beta is equal to mu naught I over 4 pi r, and here is sine phi 1 plus sine phi 2. Okay, so this was our expression. Okay, so here was point P and it was distance r. Okay, so now what happened, let's suppose that this straight line conductor have infinite length. Okay, we don't know how much hard length it is. If it has very large length, length is continuously increasing, so what, this angle will also increase, this will come like this, like this, like this. Okay, if length is continuously increasing, it means what, theta 1 and phi 1 and phi 2, we are supposing it is nearly at 90 degree, because length is so increasing, and length is increasing in such a manner that the distance between that point where we are going to calculate the magnetic field from that particular conductor, that is very small. Okay, so we will take this 90 degree. So here we got our equation that we are going to, you know, that we are searching that this 4 pi r, and this will become mu naught I over 2 pi r. So this is the expression, guys. Any kind of the question if you got in your life, okay, which ask you that what is the magnitude of the magnetic field around we can say around a particular straight line conductor, you can, by using this expression, easily you can get. Okay, what you have to know, you have to know the value of current, okay, that is flowing through that particular conductor, and also the distance, at which distance the particle is present from the conductor. So this is our expression. So I hope you like this video. If you like our video, then give a thumbs up and do subscribe our channel.